Hello everyone, my name is Prince Bandari. In this video I'm going to show you how to perform the Triaxial UU test. Before we perform any test in the lab, we should wear all the required PPEs, personal protective equipments, to be safe from all the possible risks associated with the test. For this test I'm going to wear dust mask because I will be preparing soil sample. Safety glass and the gloves. So these are the three required PPEs for this test. Let's move forward. Alright, so this is a sample preparation mold which we use to compact the sample for the Triaxial test. For the Triaxial test we require a sample size of 100 mm in height and 50 mm in diameter. Before we compact the sample, we have to prepare a soil mix is required. Here I have prepared the soil mix using kaolin and some water. Once we prepare the soil mix, we can use a funnel to place that soil mix into the compaction mold to avoid the wastage of the soil particles. So once we place the soil mix into the compaction mold, we have to compact the sample until we get the specimen of required size, that is 100 mm in height. So as we compact the sample, we have to extrude it now. So you can see the sample is extruding now, is coming out of the mold. We have to do it very carefully, and this is the prepared sample as you can see in the video. Alright, so this is the compacted sample that we got from the compaction mold. The next step is to make sure that the height of the sample is exact 100 mm in height. What happens is sometimes during compaction it may be difficult for us to achieve the exact height of 100 mm, so the height may differ, like sometimes it could be short, sometimes it could be little bit more than the required height, that is of 100 mm. So but always it is good to have bit of extra height during compaction, because we can easily cut off the extra portion later, whereas if it is short it may be difficult for us to achieve that required 100 mm of height. So always make sure that you compact in such a way that you can get bit more extra height than 100 mm, so that we can cut the extra portion later. So to do that we should use the split mold as you can see here. So these split molds will go around this sample like this. So 3 of them are enough for this sample. So we will use these 3 split molds like this. We put around the sample, and to secure these split mold, because they might fall down easily as they are not secure, so to secure them we use this metal ring as you can see. So this metal ring will go through the sample, and then it will hold the split mold. So as you can see here, the sample is little bit more than 100 mm size, so we have to cut the extra portion out of this and make it smooth. So we can cut the extra portion using the sharp knife, but always make sure that you should be very careful while using these sharp instruments. So always secure your hand, and always do it carefully. So how we do it is we just have to shear it, just slowly and carefully, just shear it like this, slowly, nice and slow, and make sure that you don't make any damage to the sample. So always do it slowly and share it again, and that's it. You can, because this is a kaolin soil, so it is very sticky, so we can just slowly tap it slowly and make it smooth like this. You can just again share it and make the sample smooth, so that we achieve the exact required height of 100 mm. Just a few more times. And once again, I'm saying that if you're using any sharp object, be careful. It may cut your finger. It may cause injuries. So be careful while using these sharp knives in the lab. And if you got injured, you have to always report to the lab techs, and they will help you through the first aid measures. Alright, so this looks okay now. So as you can see, we have achieved a perfect sample of 100 mm of exact height. Alright, so now we have got the exact sample size of 100 mm in height and 50 mm in diameter. So now the next step is to place this rubber membrane around the sample, because we will be applying the cell pressure using water. So we have to make sure that the water doesn't go through the sample, otherwise it will damage the sample. So to place this membrane into the sample, we will use a cylinder kind of device. Here you can see in the video. So we will just place this membrane inside this cylinder, just in a way that the half of the membrane will stay at the top and half of will stick out from the other side. So just place it like this and use your finger to stretch it all the way up to the halfway through the halfway of the cylinder. So once you do it at the top, similarly repeat the same process at the other side and just stretch it. So you can see it is halfway from the top and halfway from the bottom. Now if we try to place this sample into this cylinder, it will not go inside, because as you can see, the air trapped inside the between the membrane and the cylinder is causing some disturbances in the membrane, or we can say it's causing some deformities in the membrane. So it will be difficult for the sample to slide through the membrane. So we have got this tube for a reason, and we will use this suction device which will suck the air trapped inside it easily. So we have to just press it and then put this into the tube and release it. So it is sucking the air outside. Now we can easily see that, oops, sorry, let's do again. Just press it, put it inside and release it. So it is sucking the air. So I can see that the surface is now very smooth. So if we try again to put the sample inside, it will easily slide in, as you can see. Now we can take this out. After this, we will use porous stone on the both sides. As we all know that the porous stones are used to release the pore pressure or the water pressure. So we will just place this one at the top and one at the bottom. and then you can just fold the fold the membrane up. Similarly, we can fold the membrane on the bottom side as well, so it's very easy. That's all right. It might drop, we can just place it again, the porous stone, and it will easily fit it inside, so that's not a big deal. We can adjust the porous stones anyway into the at the top and bottom of the sample. So now you can see it is ready to be placed into the machine, which I will explain further. Alright, so we have prepared the sample for the triaxial test. So before we start the test, I would like to show you the triaxial test setup. The triaxial system is comprised of different parts, mainly the loading frame, which you can see here. This is the loading frame. The second is the triaxial cell, which we will assemble it here later and apply the cell or confining pressure using water. And the third one is the volume change pressure controllers, which you can see here. We can simply call them pressure controllers, which are used to apply the back pressure or cell pressure. Alright, now let's go through the different ports available here in the lower platen. So you can see here we have got four major ports, this one, this one, this one, and at the back this one. So let's start with the function of this port. So this port is connected to the top cap here. So the top cap will sit on the top of the sample and provide the pressure and apply the pressure at the top of the sample. And you can see here this port is connected to the tube. So this tube will carry the pressurized water from the pressure controller to the sample and apply finally through the top cap. So this port is used to apply the top cap pressure, whereas the middle one, this port is used to apply the cell pressure. So again the same thing, the pressurized water from the pressure controller will come through this tube, and then as you can see there is a hole here. So this port is connected to this hole and it will apply the cell pressure, the confining pressure through this port. So once we put this triaxial cell here like this, so there will be water inside the cell, and from this port, from the cell pressure port, the pressurized water will come and it will apply the pressure. In this triaxial test, we can do like multiple stage pressure. We can apply the multiple stage cell pressure like 25 kPa, 50 kPa, 100 kPa at once. So we can apply the multiple pressure at once using this port. Where is this last this one, sorry, where is this one? The right one is the pour water pressure port, which will provide the pressure at the back or at the bottom part of the sample. So as you can see, this is connected to the this platen here where the sample will sit. So there is a hole here, so the pressurized water will again come through this port and then will apply the pressure at the back of the sample. Also you can see here the main advantage of triaxial test is we can measure the pour water pressure easily. So here we have got this transducer, or this or you can just say sensor, which will measure the pour water pressure in the sample. So this is one benefit of the triaxial test. And this valve here, this valve is used to release the trapped air inside, because if there is some air inside, then if the sensor might not give you the exact reading. So once you do the test, you have to release the trapped air inside, and then it will become saturated. And finally there is one more port at the back. This is nothing but just used to fill the triaxial cell with water from the overhead tank. Okay, now let's learn about the pressure controllers. So the pressure controller we have here is a highly advanced one. It can it can apply the pressure from 0 kPa to 2000 kPa. So it has got three major parts. So one is the servo controller. This is the servo controller, or we can just simply say it as a motor. This is a motor, this is a rod, and this is a cell or chamber which has got the piston inside. So how it works is, we have got the control panel here, we have got keypad here, so we can set the required pressure using this keypad, and once we enter the required pressure, the motor will run. This motor will rotate this metal rod, and this metal rod is connected to a piston inside the cell. So this cell will be filled with water. So what happens is, now the motor will run, and the rod will rotate, and it will apply the pressure to the water through the piston. So it will push, so water is inside the cell, so it will push, the piston will push the water inside, and the pressure will be created, and that pressure will come through this tube and apply through the port there, as I explained before. So I'm again saying, I would like to say it again. It has got three major parts. One is motor, the metal rod, and the cell or chamber. So inside this chamber there will be water and the piston. So once we set the target pressure here through the control panel or the keypad, and run the motor, so the motor will run, and this will rotate this rod. So this metal rod is connected to a piston inside this cell. So once it starts moving the rod, it will push the piston towards the right side. So as the piston moves towards the right side, the water inside this cell will be pressurized. So the pressurized water will be produced. So, and that pressurized water will come through this tube and then apply to the sample. So this is just a simple working mechanism for the pressure controller. Alright, so now we have got the prepared sample. We will just place this sample with the rubber membrane, as I prepared before, into this platen. Just put it slowly, and then we can just take this cylinder out and place it somewhere here. So now we have to stretch this membrane and try to fit into the platen. And remember, we have got two porous stones on the top and bottom part of the sample. So we'll just stretch it carefully and then fix this sample to the platen. Alright, so you can see here, this is perfectly done. Alright, so now we have to put the O-rings, as you can see here. So these are called the O-rings because they look like letter O. That's why they are simply called O-rings. So the main reason behind putting the O-rings into the sample at the bottom and top is so that the water, because we will fill the cell with the water, so that water might go into the sample or pass into the sample through this bottom or top. So we have to make sure that this membrane is really tight. So to make sure that it is really any water doesn't pass through the sample, we have to use the O-ring. So you will see it. So we have got this device here. So we will try to fix the O-rings into this device. It's a bit difficult, but if we do with a proper technique, then it's easier. You know, at the beginning definitely you will find it a bit difficult, but once you practice more and more, then it will be easier for you. So one is in. Similarly, we'll put one more. You just have to use the right technique. Just drag it, just drag it, just drag it, almost there. Just hold like this and just pull it backwards, and it will be easily in. That's it. So as you can see here, we have successfully put the O-rings into that um, O shape cylinder kind of thing. So now we just slide this through the sample, because as I told before, we will put two O-rings at the bottom and two O-rings at the top. Just hold this slowly and then release it. Release both of them at the bottom of the sample like this. That's it. So this will make the membrane very tight so that the water doesn't come up. So now for the top part, we'll just put these O-rings through this top cap. Just easy. This one is much easier. One is in, second one is also almost in, I'll say. Yep. That's it. Now we can just put this top cap here at the top. Just do it slowly, nice and slow. Stretch it with your hand, and that's it. So the top cap is there at the top now. We'll just bring this O-ring easy and again try to drag it. We have to do this part very carefully because it may damage the sample. That's it. One is in. That's it. Now the second one, same process. Just slide it through. Once you practice it more and more, then you will develop the technique. So that's it. Is in. Don't place these O-rings, into the sample because it may damage the sample. Now just fold this membrane. And one very important thing is that we have to remember always while putting the O-rings, the top O-rings will have to sit around the top cap, and the bottom O-rings has to sit around the platen. Never put the O-rings around the sample as it might damage the sample. So next stage is to put the triaxial cell around the sample. While doing so, we have to be very careful as the triaxial cell is a bit heavier and is made up of glass, so always ensure that you hold the triaxial cell with your both hands. So again, while putting these, there are three groups here, so always make sure that these three groups will fit into these bolts. So slowly place it down, slowly push it down, that's it. And you have to match these groups with these bolts, so just if it's not matching, just rotate it and then it will match, that's it. And just pull this upward and tighten it, pull this upward, tighten it. It's just simple, just tightening the bolts, that's it. So once we hand tighten these bolts, we have to tighten this a bit more using the wrench. So just give it a final touch using a wrench and tighten this a bit more so that the cell doesn't move during the experiment, and do it very carefully, that's it. So you can see here I have already fixed the dial gauge, which will measure the vertical displacement as I told before. So once we set everything, then we have to set the dial gauge to 0, and then it will give the reading when the sample will displace. We will fill the triaxial cell with the water now. As you can see here, we have got the overhead tank here with the water. So we will open the valve here and the water will pass to the triaxial cell. So now we can see the water is filling. Let me give you a closer look. So here you can see the water is filling now, and at the top you can see here there is a small valve, screw like valve. So when the water is filling, make sure that it is open so that the trapped air inside the cell is released. So once we fill the water, we have to close it again. So just let it open when the water is filling. The water has been filled inside the cell, as you can see here. Now we have to do a couple of checks before we start the software. First of all, we have to make sure that the top valve is closed, as I showed before. I'll show you again. So here you can see the valve is closed. Second thing is, make sure that the back pressure valve and the pore pressure valve is closed, and we can leave the cell pressure valve open because we will be applying the cell pressure. Other thing is, make sure that this load cell is almost touching the loading ramp, and the dial gauge should be 0. As you can see here in the screen, we have set the rate as 1 mm per minute. Vertical displacement is almost 0, that is the dial gauge reading, and the load cell value is 0. So now we can start the test using the software. Alright, so once the sample is set up into the system, we can use the software to run the test. So here I have opened the software, stress path triaxial testing system version 3.11. So once you open the software, we will get this window. So here we have to put some details about the specimen using some modules. So here we will use the first one, GVT50123-1999-UU.DLL. that is the module we have to select. Specific gravity, that is 14.7 for my sample, of course kilonewton per meter cube. Job reference number 1, sample name, just put triaxial test, triaxial test, and mass is 355 gram, and that should be fine. The initial height is already set as 100 mm and the diameter is 50, and the ram diameter, the loading frame diameter is 16 mm. So once you press set, it will open this new window where we have to define the different loading stages. So in this test we will be applying three different pressure stages: 25 kPa, 50 kPa and 100 kPa, or you can do like 20, 50, 75, as much as you want. It depends on your choice, but in this test we will be using 25 kPa, 50 kPa and 100 kPa. So we all know that the main purpose of this triaxial test is to find the shear strength parameters of the soil. So we have to draw the Mohr circle and the failure envelope at the end. So at least we need to draw that failure envelope, we need at least two circles. But here, to be much precise, we can use at least three circles. We can draw three circles and draw the failure envelope and find the value of cohesion C and the angle of friction phi. So here select the standard triaxial test. We can create the stage now, 1, 2, 3. So first stage, of course, UU test. Here UU test. The target for the first stage is 25 kPa. The loading velocity is 1 mm per minute. Press next. Here the maximum the maximum axial load is 4 kilonewton. That should be fine. That means the test will terminate when this load is exceeded. Similarly, maximum axial strain is we can put 10 percentage for this one. That means once this upper strain value is exceeded, the test will terminate. Always keep in mind that the load cell we have here has the capacity of 10 kilonewton. So don't put more than that, otherwise it will damage the load cell. So always while putting the maximum axial load value, put less than 10 kilonewton to be in the safe side. Excuse me. Now add to the test list, and similarly for the next stage, the target is 50 kPa. 50 kPa, loading velocity is 1 as before. Press next. Maximum axial load 4 kilonewton, that should be fine. And the strain we can put 20 now. For the second stage, maximum axial strain 20%. That means once the sample reaches 20% of the 20% strain, the test will terminate. Add to the test list. Similarly for the third one, the target is 100 kPa. Loading velocity is same as before, 1. Maximum load is 4, that should be fine, and maximum axial strain you can put 30. So at the end of the third stage, once the sample reaches 30% strain, the test will terminate. Add to test list. So now everything is ready. We can go to test. Here we can choose the graph axis, what we want to see. Just select browse live data options, and then we can select what we want to see in the graph. So here I want to see in the graph 2, I want to see, let's say, cell pressure in the x-axis. In the y-axis, in the first, we have two y-axis here. So in the first y-axis I want to see the deviator stress. Deviator stress is nothing, just the difference between the axial load in the cell pressure. Okay, so that means the axial stress in the cell pressure. So here in the axis 2, I can just select test time, and that's fine. Okay, now we can run the test, start the test. That's it. So once the test is started, you can see here the pressure controller is doing its job. So now you can see the pressure here is increasing. So it will increase until 25, and once the cell pressure reaches 25, then only the axial load will start. So you can see here this motor is rotating the metal rod, which is pushing the piston, and the piston is pressurizing the water inside this chamber. So you can see here the pressure is increasing. Easy. You can see here the graph is coming now. So here we can see I have changed the stress to the second one. We have to keep monitoring this deviated stress curve. As soon as you find that the curve is getting constant, almost constant value, or is decreasing, we have to change it to next stage as soon as possible. So once we change to next stage, the 25 kPa will increase to 50 kPa. So, and once it reaches to 50 kPa, the axial loading will start. And again, we have to keep monitoring this curve and the axial strain value. Once you find this curve is getting a constant value, almost constant value, or is decreasing, we have to change it to the third stage as soon as possible. So here you can see that this curve is getting almost a constant value, so we can change it to the third stage now. Here, change it to next stage. You can see the axial load is decreasing now and the cell pressure is increasing. So now for the third stage, we will let the sample to fail, reaching its maximum axial strain value of 30%. So we can see here the test has been terminated. If you focus on the value of axial strain, the value has reached 30.03%. That's why the test has been stopped. So you can see here we went up to 25 kPa cell pressure. The deviator stress increased, and as soon as we shifted it to the second stage, it again increased, and as soon as we shifted towards the 100 kPa, that is the last stage, third stage, it's again increased, and at the end, once the axial strain reached 30%, which is the maximum strain, the test has been stopped. So in this way we have got a curve here. So now we can export these values easily to the Excel file and draw our own graph as well according to the need. So now the next step is to export these results to the Excel file, or save it first. Just go to the top menu bar here. We can see file, control, view and help. Just press control and select data conversion. It will open this window box, and select the first one and press open. It will save the file to that directory. So now if you go to that directory, which is this one, and open it, so it will show you all the mixed data here. Just select all and copy it, open the Excel file. It will take some time. Just select here and open the Excel and just paste it here. So now you can see we got the Excel file here. We can easily draw the graph according to the requirement. So here, let's say we can see the value of axial displacement here and the load cell. So we can draw the load versus displacement graph as well, and also we can easily find the maximum load cell value or the maximum displacement value. So in this way we perform the triaxial test. So in this way we can just draw the graph according to our requirement, and based on the value of stress and shear strength, we can plot the graph, plot the Morse circle and find the failure envelope, from which we can find the value of cohesion and the angle of internal friction phi. So it's very easy process. Triaxial test is a very easy and quick process. So I hope you guys understood it well. So once the test is finished, we have to drain out the water inside the triaxial cell. So we can just use this tube to drain the water safely into the bucket. You can just open the top valve and then open this shell pressure valve and just drain the water. As you can see here, water is coming out from this drainage and is ending up to the bucket. So once we drain out the water, then we will take out the sample and see the failure mode, how it has failed. Alright, so I have removed the failed sample from the triaxial test setup once I drained out the water. So after that we can see the failed sample and interpret the failure modes. So here you can see the sample has failed from this plane and from this plane. So this is the shear failure. As the load was applied, the sample tried to fail in shear. You can see like this. So this part has been sheared out from this part, so it is a shear failure. You can easily see you can clearly see the failure plane as well. So this is how we do the test. Thank you everyone for watching this video. I hope you guys enjoyed the test. If you have any questions or doubts about the test, please feel free to consult your supervisor, or please feel free to consult lab techs at Civil Engineering Lab here in Melbourne campus. You can contact the lab techs by an email. You can contact myself, Prince Bandari, at this email. My email is p.bhandari@cqu.edu.au, or you can contact Rag. His email is r.vasudhya@cqu.edu.au. Thank you everyone. Stay safe. Take care.